Hello, I'm Donald O'Hara. This is my presentation for Lab 3 for Principles of Physics. So in this lab, we use GlowScript to simulate the orbit of a star around a black hole, and then use the data to calculate the mass of the black hole. And then the second part was we tried to simulate a figure-8 orbit of a ship around a moon and a planet. This is for part 1, the star and the black hole. The initial conditions were unique based on your email. So this initial velocity was related to the change in momentum as it was iterated through in the while loop by the given mass of the star. So then this change in momentum is equal to the net force. So then we found the parallel change in momentum by finding the unit vector and the magnitude for that, multiplying them together, and then that is equivalent to the parallel net force. And then we found the perpendicular net force by subtracting that from the overall net force. So since the only force acting on the star was the force of gravity by the black hole, we can work backwards and algebraically find the mass of the black hole based on the force of gravity. So the mass of the black hole is the magnitude of F net times r squared divided by the mass of the star times the gravitational constant. And then it printed out this mass every time it iterated through that while loop, so hundreds of times. And this data was averaged out to the number below, and then the mass of the black hole based on that data is 1.0694 times 10 to the 44 kilograms. So net force and the rate of change of momentum and their parallel and perpendicular components are technically different concepts, but they are mathematically equivalent in scenarios where mass is constant, like this one with the star. So this allows us to take raw data like velocity and position that we get from, say, observation or computation, and connect it to these net force calculations, and that allows us to come to conclusions like finding the mass of the black hole, things like that. Part 2, this was the planet, the moon, and the ship. So we again use the equation for the force of universal gravitation to calculate the net force on the moon and the ship. So the net force was used to update the velocity, and the velocity is used to update the position iteratively. So the forces acting on the moon were the force of gravity by the ship and the force of gravity by the planet, and then the forces on the ship were gravity by the planet and the moon. And there was a lot of trouble trying to find a figure-8 orbit for the ship. It was very difficult. There was no clear conclusion. So the glow script was really finicky. I feel like I had to comment out a couple of like lines like where it ended the loop if you collided with the moon, and eventually found that the circular speed of the moon around the planet is about 24,000 meters per second, and then the ship would have to orbit the moon at about 14,000 meters per second in the negative x direction, because that was the way the moon was moving, and then 24,000 in positive y direction. So that was the initial velocity that I set it for, and this did actually result in a, I believe, stable orbit of the ship around the moon, even though it kept saying that I crashed into the moon. This was the best I managed to do. I couldn't get a figure-8 orbit, honestly. So this question asks, what if there was a black hole, star, planet, moon, and spaceship in one system, essentially combine the two parts? So to predict the motion of the system, you'd have to go to every object and calculate the force of gravity by the other 4 objects on that one, and then do what we did before, update velocity and position. And the black hole and the sun would likely totally dominate the interactions due to their huge mass, which would give them much greater gravitational force than the other 3 objects in the system. And they would likely, the star, planet, moon would probably be negligible on the star. I'm sorry, the planet, moon, and ship would likely be negligible on the black hole and the star. And it would basically just be observing what happens between those 2 massive objects.